Welcome everyone. Welcome to one more telecom seminar, which is hosted by the Technology Innovation Institute in Abu Dhabi. I'm Dr. Leonard Acosta. I'm currently a principal researcher at TII. And for today, it's a great pleasure and honor for us to have Professor Roberto Verdone as the speaker of this seminar. Since 2001, Professor Roberto Verdone is full professor in telecommunications at the University of Bologna, Italy. In 2001, he founded a research group, Radio Networks, working on radio resource management for mobile systems, MAC routing and topology of wireless sensor networks, architectures and technologies for the IoT. He is currently active in the field of industrial IoT, 5G, and beyond 5G systems, using terahertz communications and UAV-aided mobile radio networks. Since 2020, he's director of the CNIT, National Laboratory of Wireless Communications, YLAB, which has around 90 researchers. And since 2021, he is also co-director of the WiLab-Huawei Joint Innovation Center on Intelligent IoT for 6G. He published about 200 research papers on IEEE journals and conferences. So in his talks, in his today talks, he will focus on industrial automation and factory networks, as they are going to become a very important application area for 6G. So basically the talk will analyze what can be done with 5G and what we require a new generation of wireless networking using higher frequency bands and more flexible topologies, AI-based protocols, and network architectures. Thus, Professor Roberto Verdone, once again, thank you so much for accepting our invitation. And without further ado, the floor is yours.
Thank you very much. Thank you very much for the introduction, but in particular, thank you very much for the kind invitation to this telecom seminar series you have at TII. Okay, so I've been already introduced. By the way, yes, we had 90 researchers at YLAB, the laboratory of wireless communication I'm directing in Italy, a couple of months ago, but now it's more than 110. And this gives you an idea of how much my lab is growing thanks to the many projects we have from European funds, from national funds, from companies, and so on and so forth. This is the title of my talk today, 6G for Factory Networks. Actually, I would like to share the fact that there are many people at YLAB who are currently working on industrial IoT, factory networks, and their names are reported here, just to thank them for their activity, which supports my speeches. A few words about the institution I'm directing, YLAB, which is the National Laboratory of Wireless Communication of CNIT, which is an international consortium, an inter-university consortium of for telecommunications. So CNIT gathers together all universities in Italy. YLAB, as the National Laboratory of Wireless Communication, gathers together people from 8, 9 different universities. You see the names here. But the headquarters of YLAB are in Bologna, my city. What YLAB deals with is 5G, 6G technologies, the Internet of Things, applications, verticals like Industry 4.0, vehicular communications, and so on and so forth. We are used to say that since when it was funded 3 years ago, YLAB is the Italian home of wireless. We have a lot of projects on the area of wireless communications. We are also co-founders of the 16G Association, which is the association gathering in the past 2 years about 90 members. Many of them are major stakeholders in the field of telecommunications. And the 1.6G Association has the scope to support the 6G standardization that, as everybody knows, will start in 2025, from the viewpoint of the application of 6G to the different verticals. We have many partners involved in our research areas at YLAB, but I would like to mention in particular one today, which is BREX. While the technologies, the concepts that I will describe today come from projects we have with Nokia, TIM, Huawei, and other companies. However, BREX is a very important stakeholder. BREX is a national center of competence funded by the Ministry of Economic Development in Italy. It's centered in Bologna, again. Actually, their premises are just one floor from the premises of YLAB. But the most important fact is that BREX is a consortium gathering all major companies in the automation industry of Italy, which, by the way, most of them are in the area near Bologna. It's like 30, 40 different companies. YLAB, my lab, has a memorandum of understanding signed since 2 years with BREX, and this allows us, on one hand, to have continuous discussions with the CTOs and the CEOs, the managers, and the technical staff of these big companies in the field of automation industry. And on the other, we can use the BREX pilot space, as they are calling. You see pictures here, which is a huge space where many machines, automation machines, are available to us to make experiments. So in other words, through the cooperation with BREX, we have the possibility to talk to companies in the field of automation industry. And so many of the things that I will mention come directly from the talks I have regularly with the managers of these big companies. To mention some: Philip Morris, GD, EMA, IMA, and so on and so forth. Also, we have companies in the field of automotive which belong to BREX. So they are all companies to whom we are used to talk very frequently. So let me now start by describing the architectures that we have in mind when we talk about the factory of the future. A factory that would be equipped with 5G and 6G and/or 6G wireless systems that should possibly cut the wires, or in any case complement the current communication capabilities of automation machines, which are nowadays, as you know, based on Profinet, Ethercat, and other wired technologies. The scope of the inclusion of 5G and 6G in the world of automation industry is to provide much better services through the possibility to use wireless. There are different scenarios that we are discussing with the companies I mentioned. On one hand, the simplest one is the one where you replace wired technologies that currently connect sensors and actuators over industrial machines to the local controller, the PLC, implementing a 5G, 6G network over the machines so that the communication between sensors, actuators, and the PLC can happen via 5G or 6G. But this is one of the simplest scenarios we are considering. Other scenarios that we are discussing, for instance, with companies that build PLC, consider the possibility to have remote PLC, which are connected via 5G and 6G to the automation machine. What's the advantage of remotizing the controller? The advantage is that with one unique controller, you can control several machines, for instance. Also, the controller might become a software-defined entity, which is easier to maintain and to update. But of course, it requires a high capacity link with the machines it is controlling, and this might happen via 5G or 6G. Other scenarios are those where multiple machines are interconnected via 5G and 6G, for instance, for control-to-control applications. And finally, but this is really a long-term scenario, we might consider a unique controller responsible to control all the machines in an industry plant. This set of architectures are the scope of our research, which sometimes take the path of very experimental research, sometimes of more theoretical research, as you will see in my talk. When talking about when talking about industrial automation, we can not avoid talking about the documents delivered in the past years by the 5G SAA. The 5G SAA, it is very well known, is a consortium of all major stakeholders in the fields of automation industry, which delivered in the past years documents, white papers, which were considered as inputs for the standardization of 5G. Among them, some white papers described the different sets of applications and use cases which are of interest to the stakeholders in the field of automation industry. This slide here is taken from one of his documents. It shows 5 rows, which are the different types of applications of the industrial automation, and 10 columns, which classify different types of use cases. Now, based on the discussion we are used to have, as I said, with big companies in the area of Bologna, which are gathered by this consortium, BREX, we realized that to most of these companies, when talking about their medium-term goals, so in the coming 2 to 5 years, they are interested into the application of some specific use cases, which I have emphasized here. And in particular, they are interested into control-to-control and mobile robots. So the rest of my speech is dedicated to these 2 types of use cases, control-to-control and mobile robots, in the specific field of application of which is the so-called factory automation. The 5G SAA has also discussed a number of potential network architectures which might be used in industrial context. I'm reporting here again a figure taken from the 5G SAA white papers. I'm not going to comment on all different possible network architectures. Just let me mention that, however, my personal feeling after the discussion in the past 2 years with these companies is that so far, even in the medium long term, they still see as a unique case of interest, the first one you see here on the left-hand side, where the machines, the mobile robots are connected to the 5G or in the future 6G network, where the PLC might be implemented, but not wirelessly. They still consider the other scenarios, in most of the cases, as rather futuristic. So this is our baseline scenario, which, however, has a number of potential options, and I will describe 2 of them. So after this quick overview on the different use cases, and in particular the ones of interest to our research at YLAB, let me spend a few minutes in summarizing what are the basic requirements for 6G future factories. Again, I'm putting together elements which you find in papers, in research fora, but which are also the result of the discussion I had with the CEOs and CTOs of these big companies. From the viewpoint of the requirements for 6G, for future factories, well, we can represent them through a 5-pointed star, because 5 are the most relevant requirements which are needed which will be the base of 6G standardization, having specifically in mind future factories and in particular the industrial automation field. One is the battery duration. These people will be ready to accept that sensors and actuators over machines will be wireless as long as it will be also possible to cut the wires connecting the sensors and the actuators currently to the electrical grid. So these devices need to be battery driven, and they don't want to change the battery, replace the battery more often than every year. And this is, to me, maybe the most difficult requirement to face, which might have a number of implications from the viewpoint of the protocols that will be needed to be included in 6G, which are not in 5G, but I'm not going to discuss this in this talk. Latency. It is very well known that the end-to-end latency that can be offered by 5G currently is in the order of few milliseconds. 1 millisecond for the air interface, as long as the URLC component of 5G will be available. But in terms of end-to-end latency, so including not only the air interface, but also the core network, it sums up to 2-3 few milliseconds. Now, in terms of the latency requirements of the industrial automation use cases, some of them require latencies like 5 to 10 milliseconds. So 5G is perfect. Some of these use cases require sub-millisecond latencies. And for this, we definitely need to wait for 6G. In terms of throughput, this is an estimation of the requirement needed for some use cases. In terms of reliability, whenever you talk to people managing automation industry plans, they say, we are used to communication technologies on wire, based on wires, that provide to us a reliability with 9 nines, which means 99.99999% is the probability of success of any transmission. So 10 to the minus 9 is the block error rate. Well, we want to have, they say, the same reliability with wireless, which is something which 5G doesn't provide yet. And so for this, we need 6G. And then the fifth requirement is in the location accuracy. It is well known that 6G will implement the ISAC concept, integrated sensing and communication, which will allow, while communicating, to localize the UEs in the environment. And this is essential for the industrial automation, as long as it will be possible with one unique system communicating with the device, also to localize them. But this requires an accuracy which should be between 1 centimeter and 0.1 centimeter. So it should be millimeter oriented localization. And this is another aspect which possibly will be available with 6G, not with 5G. Now, let me describe 2 future factory network use cases that we are currently studying since several months, or maybe even 1 year at YLAB. One of them is more of experimental, has been assessed and discussed more from the experimental viewpoint, the other one more from the theoretical viewpoint. You can take these 2 examples as examples of what can be done with 5G and 6G in future factories, and examples of what we are currently studying in agreement with some of the stakeholders, in cooperation with some of the stakeholders that cooperate with YLAB, like TIM, Telecom Italia, Huawei, and the industry automation companies that I was mentioning earlier. The first use case I'm considering deals with the field of mobile robots. In particular, here we are considering, from the experimental viewpoint, an AGV. You know, an AGV is a robot that moves and is used normally to carry goods, and based on some path which for which it is pre-programmed, the AGV moves in the industry area. And of course, it has sensors in order to detect whether anything happens unexpected, like a worker which goes close to the AGV, then the AGV has to suddenly stop in order to avoid hitting the legs of the worker. Now, in this case, the experiment that we are performing, and this is done at the premises of BREX, is represented by a couple of pictures that I introduced here. You see here Niccolo, one of my PhD students. He is going to start walking, and he goes in the direction, he works in the direction of the AGV, which is moving, and it goes too close to the AGV. So the result is that the AGV will suddenly stop. And by suddenly stopping, what happens is that a bottle of water, you see it here, a bottle of water which was representing a dangerous good carried by the AGV, falls on the ground, which is bad, of course. We have to avoid this situation. How can we avoid this? Look at the sketch, the diagram on the lower part of the slide, which represents the network that we have, the team has implemented and we use within BREX premises. The AGV has been equipped by this white blocks here, which is a 5G device with accelerometers, 3-axial accelerometers, and gyroscopes mounted on it. The data is sampled every millisecond on the board, and it is transmitted to the GNOT B, which is 20 meters apart inside the BREX premises, through a 5G connection, which is based on millimeter waves. Then all these samples taken by the sensors every millisecond are sent via the GNOT B to the core network, and then to a server where we mount an AI algorithm. The scope of this AI algorithm is to predict, looking at elaborating the samples coming from the AGV, predict that the bottle is going to fall. It can be shown that as long as the end-to-end latency of the entire path from the AGV to the AI is less than 1 second, including the time needed by the AI algorithm to predict that the bottle is going to fall, it is possible to send a command back to the AGV in order to avoid that the bottle will fall. So the full sequence of delays which are included in this path from the AGV to the AI should be less than 1 second. So the end-to-end latency from the AGV to the AI should be less than 1 second. What are the elements that sum to contribute to this end-to-end latency? There's a number of delays. It's this first sum over I of tau I. There's a number of delays which are easy to assess. They are deterministic or mostly deterministic, like the processing time of the GNOT B, the core network, and so on and so forth. They can be easily estimated. Then we have to add on top of this the time needed to access the air interface, which depends on the scheduling of the GNOT B and the protocols implemented at the GNOT B. And this is random. It's random, but of course it can be somehow controlled as long as you put the hands on the protocols, on the software stack, and you can try to keep it under control. And then there is a third contribution in this formula, which is tau AI, which is the time needed by the AI algorithm to elaborating the samples coming from the AGV to predict that the bottle will fall. As long as the sum of delays is smaller than 1 second, we can send a command to the AGV and avoid that the bottle will fall. Now, as you may notice, this has the simple consideration has a number of implications. Let me emphasize one. The possibility to really implement this use case depends on the integration of a number of facts. One is how large is the sum of tau I, which means what is the network architecture. For instance, in this case, the AI is after the core network, but we might even implement it closer to the G node B. So on one end, there are network architecture issues. On the other, there are radio protocol issues, like the time to access the G node B, which depends on the scheduler. And finally, there is the AI element and the time needed by the AI algorithm to implement the prediction. So we are currently comparing different AI algorithms. We are currently implementing different network architectures to check which combination will allow to remain below 1 second. This is an example of what we are doing at YLAB, and I can tell you that either with a network architecture like this one or the other network architecture that we are considering, where the AI is closer to the G node B, we found a combination of algorithms and protocols which allows to determine within 1 second to have an end-to-end latency which remains under or close to 1 second. So in other words, this use case can be implemented as long as you choose properly the algorithm, the network architecture, the protocol stack, and you use a 5G millimeter wave radio access technology. Let me move now to the other use case I want to mention in this speech, which is control to control. Control to control is an application where you deal with multiple machines that have to cooperate because some of the machines are implementing a production process which goes step by step from one machine to the next machine to the next machine, and so on and so forth. In this case, control to control is a use case which normally require a latency, an end-to-end latency below 10 milliseconds, in some cases below 1 millisecond. So clearly, this requires 6G because only with 6G you can go below 1 millisecond putting together the different elements. So let me describe somehow what we are doing in this sense. This is, as long as I have mentioned 6G, currently a theoretical implementation. This is done within one of the projects funded by the WiLab-Huawei Joint Innovation Center on intelligent IoT for 6G that we have in Bologna. So this is activity performed together with Huawei, which is currently theoretical, though in 2024 it intends to become an experimental activity. So in this case, the situation is the following. We model an industry plant like you see in the slide. We have 16 machines which run their task in an industry plant, and they are in a 4x4 fashion. And what happened is the following. First, 4 machines which have sensors embedded start running for some time, some millisecond. Then after 8 milliseconds in our simulations, they stop working, and there are other machines in the same production line that start working for the next 8 milliseconds, then again and again, and then this is repeated many times. The result is that we have traffic generated by the sensors, which is traffic, which is data packets sent every millisecond by every single sensor, which is temporally and spatially correlated, which is something very relevant from the viewpoint of our simulations, where we design scheduling approaches to tackle with the requirements of this control-to-control use case. One of the things that we did in the past few months is to formalize the concept of a fully aware G-Node B, also known as a smart G-Node B. What do we mean by a fully aware G-Node B? It's a G-Node B, and the scheduler is implemented as G-Node B currently. Well, actually, we are considering both centralized and distributed algorithm. I'm presenting here the case of centralized algorithm where the scheduling is performed at the G-Node B. We assume with the fully aware or smart G-Node B that the G-Node B has a number of information beyond the usual information that any scheduler receives, like the channel state information and so on and so forth. We also assume that the G-Node B has information regarding the production process, so information which comes from the PLC. So in other terms, we assume that the G-Node B and the PLC are in strict cooperation, and they exchange all the information they have. So the smart G-Node B knows about the number of production lines inside the factory, the number of machines per production line, and in particular, they know, the G-Node B knows when each machine is going to start working. And so what is the set of sensors that will request transmission of their packets every 8 milliseconds. Now, of course, the concept of smart G-Node B goes in the direction of designing and implementing optimized scheduling algorithm. Look at this slide here. For a given set of parameters, what you see here is the average end-to-end latency, which should be less than 1 millisecond, as a function of the number of UEs, the number of sensors which are present in the plant. Now, look at the lower bars, the white bars. These are the end-to-end latencies that we got through our simulations with the smart G-Node B concept. And this small number, 0% that you see on top of them, is the percentage of packets which were not scheduled in order to arrive at the G-Node B within 1 millisecond. As you can see, it's 0%, whatever the number of UEs. Of course, by increasing the number of UEs, there's a slight increase of the latency, but it's still below 1 millisecond because the scheduler has to allocate radio resources to a larger number of UEs. But now let's move to the larger bar, the dark gray bar. This is the case of a partially aware G-Node B, a G-Node B which doesn't have the information on the production processes. As you can see, of course, the G-Node B is not able to properly schedule the packets because it doesn't know when they're going to arrive exactly. And the result is the following. On one end, the end-to-end latency increases significantly, as you can see, significantly above 1 millisecond. But more importantly, the reliability of the scheduling algorithm worsens to the level that 76% of the packets which are received are discarded because they arrive with a delay which is larger than 1 millisecond. The average delay is 1.5, and 75% of the packets are received later than after 1 millisecond. Clearly, this is a clear disadvantage that we have when having a G-Node B, which is not totally aware of the information which is present at the PLC. However, there's also a light gray bar, as you can see in my slide, and this is actually the performance that we got through a partially aware G-Node B, which, however, implements some explore-exploit heuristic. Since the traffic generated by the machines during the 8 millisecond is periodic, what the G-Node B tries to do is to observe the first few milliseconds, what's going to happen, learn that a new machine has entered into play, and schedule properly for the remaining time the radio resources for the next packets. Of course, as long as a new machine will come into play, again, explore and then exploit, and so on and so forth periodically. There is a significant increase, which brings, depending on the number, increase in the performance, because as you can see, we are going now to lower values of the average end-to-end, and to lower values in the order of 11% of the packets discarded. The average performance is close to the requirement, but in some, depending on how many nodes are in the network. Of course, as you can imagine, if the number of nodes in the network is larger than 100, and it goes like 150, 200 nodes in the industry plant, the average end-to-end latency turns back to 1.2, 1.3, 1.5 millisecond, and this is not good. So, as you see, the concept of smart G0B is a very important concept, which, however, requires that the PLC and the G0B are connected or exchange information, and this is a major fact, because this means you have to define proper interfaces, standardized interfaces between some protocol entities of the G0B and the PLC, which are currently made by vendors of totally different communities. Now that we have discussed somehow some potential future use cases for factories, let me go back to the issue of the requirements for the 6G future factories. As I said, I'm used to have many talks with companies in the field of industrial automation and so on and so forth. And there's something that I want to report to you, which actually we decided at YLAB to start addressing in terms of research, as a research activity, since few months. We started actually in December. This is the same picture I've shown earlier. The main requirements for 6G for future automation industries are in terms of battery duration, latency, throughput, reliability, location accuracy. But actually, there is one requirement which is not mentioned here, which at the end of the story, whenever I meet people in the field of industrial automation, is the requirement which is mostly mentioned. And this requirement is the one dealing with data security. As long as you talk to these people saying, we want to remove cables and include 5G or 6G as a wireless technology, they always want to discuss for minutes, hours about the issue of data security. They say, I will not trust a wireless technology until it will be 100% safe from the viewpoint of the impossibility to steal the data which comes from the machines, because the data taken from the sensors on the machines are sensitive. This is sensitive data, which means that if someone will steal them, it's a value for us, which is stolen. And so we normally, when we get this kind of issue mentioned by the managers of these companies, we have to start discussing about the ways to achieve data security. Well, traditionally, there are at least 3 ways to achieve data security that might be and should be considered by 6G. First, maybe the most traditional one, encryption. You introduce a level of encryption in the digital communication link so that both in the wireless part and in the fiber part in the core network, so that nobody can steal the data. But everyone knows, and the managers of these companies know, that every day there is a hacker that can enter into some system, violate all security measures, and so they don't trust fully encryption. Second option, you know that with 5G, our telecom operators are offering as an option to the industries the concept of NPN, non-public networks, also known as private networks, where most of the network nodes, if not all of the network nodes, are deployed inside the company premises. Of course, if everything is inside, it's within the IT umbrella of the company, and it will be secure, or at least it will be secure to the level that the company is able to provide. Unfortunately, this is a solution only in few cases for very large stakeholders, because implementing a full NPN inside an industry premises is something you can do with a big company, but not with small and medium enterprises. So it's not the solution. Another solution is to discuss with these stakeholders, something we did thoroughly, about which data have to be protected, which cannot be protected. I mean, if from a machine you are measuring data from accelerometers, gyroscopes, temperature measures, humidity measures, whatever. Some of these data maybe need to be secured, but some of them don't have any kind of relevant value. So why not at least work on the latter? And the answer that very often these managers provide is no. It's too complex for us, a big company, to tell to the IT department which data are to be protected and which cannot be protected to the highest extent. And so typically the IT departments say, no, we want to protect all data. So neither of these three options is the solution. Maybe a sort of a synergy among them, an integration of them. But what we are starting addressing now is something that I used to call data security by architecture, which is a concept which is somehow related to the concept of federated learning. Let me describe what I mean by data security by architecture. Consider the upper part of the slide, where a machine, whatever is the type of machine, is equipped with 5G and in future 6G devices that with a number of sensors take data which have a value from the machine. This data is sent through 6G and it goes to the PLC, and then commands go back and so on and so forth. Now let's go to the lower part of the slide. Assume that we implement a neural network at the machine level. And this neural network, which is a machine learning agent, trains and is trained and elaborating on the data, determines a model of the machine, and this model is sent via 6G, not the actual data. Now, what I mean by a model, a neural network, as you know, is a network, a software entity, which has a number of parameters to describe it, to describe the model, which can be very large, in the order of tens or hundreds of thousands of different parameters. So it's maybe 50, 100 megabytes of data. Now, assume that rather than transmitting to the AI the data themselves, so the data taken from the sensors, you transmit the neural network parameters. So the data is not transmitted. It remains on the machine. And so this architecture is inherently secure. Of course, we might discuss whether stealing from the transmission, the neural network parameters, we can go back to the original data. The answer is no. Of course, if you can read the neural network parameters, there's some information in it which relates to the data, but it's not a full information. So we believe that this concept of transmitting the neural network models very frequently, and of course the centralized AI will send back new models and so on and so forth, this paradigm integrated with the others, can reach the level of data security which is requested by these companies. Of course, this concept, as long as we are not considering one unique machine managed by one AI in the network, as long as there are multiple machines and so multiple UEs, this concept is close to the concept of federated learning, where actually multiple local agents can provide their models to one centralized agent, which will send back to the local agents a new model based on the aggregation of the information. And so every local agent can take advantage indirectly of the training, the learning made at the other agents. So as long as you have a multiple UE scenario, the concept I was introducing as data security by architecture becomes, in particular, the case of federated learning. So we hope, and we are currently working on some projects financed by the national government, and with experiments we are starting at BREX premises. We hope in the next few months we will be able to convince the managers of the industrial automation companies we talk to that through this concept, data is secured. So let me conclude my speech with few slides more, just to tell you what we are going to do in the next 3 years. We are coordinating a project which is funded by the European Commission through the SNS framework. You know that the SNS framework has started in January 1st, 2023, a set of new projects. One of them is TIMES, that we coordinate at YLAB. It's a 3-year project, so just started, and the project will last for 3 years, to 2023, 24, and 25. This project has goals which are summarized by this slide. Imagine an industrial plant where there are machines, automation machines, AGVs, mobile robots. All of them will be controlled by centralized controllers through a network which will use sub-THz frequencies, will include the possibility to implement intelligent reflecting surfaces over the walls of the plant in order to create a multi-hop network where all devices mounted on the mobile robots, on the machines, will be able to be connected to the centralized controller, either via traditional multi-hop through active routers, or via intelligent reflecting surfaces. Of course, the fact that we're working at frequencies above 100 gigahertz, most probably 300 gigahertz, so the sub-THz band, make things very complex because of the path loss, because of the very complex environment from the propagation viewpoint. We will have beamforming techniques, beam focusing techniques where large intelligent surfaces will be used as antenna systems, and so on and so forth. This is the scenario for this TIMES project that we are coordinating at YLAB. Moreover, I'm also coordinating a project in industrial networks, which is a part of one big, huge program, Restart, which started on 1st of January, financed by the national government in Italy. It has a 3-year duration, so again, it's 23, 24, 25. The project has a number of objectives like the ones which I was mentioning for TIMES, but from the viewpoint of the scenarios, there are more complex aspects, like the inclusion of people that move around, so workers, and possibly even drones for mainly for the outdoor parts of the industry plants. So this is to give you a glimpse of what we're going to do in the next 3 years in this concept, in this context of future factory networks with 6G. And so stay tuned if you want to have more information. So let me conclude with a quick summary. I introduced the notion of smart G0B, or a G0B which is integrated with the controllers. And I have shown what is the role of this integration in terms of full awareness or partial awareness of the information regarding the industry plant and its processes. And I've shown that through the smart G0B concept, we can achieve with 6G performance in terms of latency, which cannot be achieved without such concept of smart G0B. Through the other use case I mentioned, the one on the mobile robot, you may remember the AGV, my student who was moving close to the AGV, I have emphasized a concept which is very important to me, that you cannot tackle with aspects related to communication without considering for industry use cases also the AI without taking into account the AI aspect as well. So whenever you talk about latency requirements, you need to take into account the network architecture, the network protocols, and the time needed by the AI to perform its assessments. And so I don't take seriously results which are only related to the network aspects, as long as, which is not true for all use cases, of course, it is not true, as long as the use case requires some important role played by the AI. And finally, we are currently investing on this paradigm of data security by architecture, which allows not to send the data, but only the models of the neural networks, which we hope will be able to convince the managers of the companies in the field of industrial automation regarding the security of the data. This is it. Thank you very much for your attention.
Thank you, Professor Roberto Verdone, for the very informative talk. Now we'll move to the Q&A section. So I encourage our attendees to write the question in the chat box. We have a couple of questions. The first question is about 6G localization. What are the technologies used in 6G localization in order to achieve a precision of 0.1 centimeters?
Okay, thank you very much for the question. In terms of localization, I will now mainly discuss the indoor scenarios, which are the most relevant in industry settings. In terms of indoor localization, there are well-known traditional technologies like ultra-wideband that can be used to localize moving objects in an environment with a precision and accuracy, which depends basically on how many anchors you are allowed to deploy in the industry environment. Now, of course, there is one problem, which is you have to deploy, and this includes a cost in terms of CapEx and OpEx, a number of anchors. And also, there is an issue in terms of the fact that in industry plants, very often, you don't want to have cables on the ground and so on and so forth for security reasons. So I believe that the technology that will be the new paradigm implemented in industrial settings is, I mentioned it, ISAC, Integrated Sensing and Communication. The basic idea is that the same waveforms that are used by the base station to communicate with the UEs are also used at the same time for localizing the UEs. In order to do so, the waveform must be designed properly, because a normal waveform, like a rectangular pulse multiplied by a sine, is not good enough in order to perform localization. time direction of arrival based localization or whatever. You need, for instance, chirp-based waveforms, which are better in terms of the ability to perform localization. So this requires that you design the waveform of 6G, jointly taking into account the localization and the communication needs. I'm not sure whether this will be done. There are trends which consider the possibility to perform ISAC in a time division way, which means the time is split into slots. During one slot, you communicate, and during the next slot, you localize. But in any case, it will be the G node B that will integrate the localization and the communication technologies and scopes, which is very much pleased by the industrial automation managers, because they, when I tell them about the future of ISAC, they say, oh, so I can get rid of one part of the problem, having one unique system for getting to requirements, which is very good from the maintenance viewpoint for us. So ISAC is the answer.
Good. I have one question, I mean, basically related to this point. What do you think about, we go a step further on the integrated sensing communication, and we include in the process the powering of the devices, because one of the requirements you mentioned is the battery duration. And usually in factory networks, some of the sensors are low power devices, and they to keep it to prolong the lifetime, we need to find some strategies. And since the wireless medium, you have a signal propagating, one of the concepts currently investigated in the literature is the energy harvesting. So it could help, but I'm not sure how challenging it would be, because in that case, we would have integrated sensing, communication, and powering. I mean, three challenging tasks in the same platform.
Okay, thank you very much. Very interesting and smart question. We are talking about wireless power transfer, also known as WPT. I'm not an expert of WPT because this is typically in the hands of people dealing with the design of antennas, radio frequency components, and so on and so forth. However, a few years ago, I had one project with one of these big companies I was mentioning where we did implement, and I'm talking about the delivery of a proof of concept, we did implement actually WPT. So I have some experience, though I don't know all the elements of the scientific community. I must say that I believe that based on the results we have at YLAB and the literature, ISAC will become a reality for industrial environments within the next few years. I'm not sure this will be true for WPT. Maybe in the longer term. The reason is, I have the impression, as I said, I'm not a true expert, but based on the expertise, based on the experience we had a couple of years ago, I have the impression that WPT is still in a phase where there are many technological problems that bring the possibility to charge the battery of these devices only as long as the transmitter is located very close to the device, so close that it tends to become almost useless if you want to integrate this in a G node B, which on the opposite should be able to cover an area like 100 square meters and maybe even 10 to 20 meters far from the devices. So I'm not sure whether WPT will be an available option in general, maybe for some niche applications in the short term. Maybe 7G. With 7G, maybe with 7G. So there is an issue actually, but it's a very interesting trend, and I would be happy to know more from the real experts.
Yeah. Okay, let's go for the second question about the next generation of Industry 4.0 and 5.0. Could you please tell us more about physically possible to have this kind of end-to-end latency? And what about the required computing power and energy consumption? I think it's the latest you show for mobile robots. I'm not sure. Yes. Could you please?
Depending on the use case I was mentioning, latency requirement in the order of millisecond, few milliseconds or less than that. This is definitely feasible. I mean, the control-to-control use case that I was mentioning is something that we are studying together with Huawei since a couple of years. The intention, as I said, is to have a prototype, a proof of concept, actually, by 2024. So it is feasible. I mean, if the big company tells me it is feasible in 2024, we will make it, I trust them. From the viewpoint of the power needed, from the viewpoint of the computation issue at the edge, so at the devices, I'm very optimistic for two reasons. First, I know that already with very simple, very well-known, easy-to-use platforms, which I will not mention, but those that any student of an engineering course has in his garage to do things. Though they're super simple, you can implement some light AI algorithm, they work properly. So if this is true with non-customized and current technologies, I'm pretty sure that with 6G, this will not be an issue at all. But there's something more that I want to mention. I'm optimistic also for another reason. The other reason is the following. Consider my paradigm where I bring the AI partially at the edge and partially kept centralized. So what is the federated learning concept as long as you have multiple UEs? What kind of AI do you need to have running inside the node? You need to have a neural network whose complexity will depend on the task you have, on the performance you require. But since the local agent has to perform only, so to say, partial elaborations, and the rest will be done with the support of the centralized algorithm, there's no need for a lot of complexity. So currently, if you read papers regarding this aspect, you read that the neural networks that have to be implemented under such paradigm include a number of parameters, which are a measure of how complex is the computation and how often and how much you have to transmit back and forth, in the order of thousands of parameters. Now, we are launching within our Joint Innovation Center with Huawei a new project that will start 1st of March, which is dedicated to a mathematical operator, which is known as GNIO, which promises to allow computation at the edge of the same type of tasks and with the same performance as neural networks, with a number of operators in the order of tens, which makes the computation much simpler and the optimization much simpler. So I tend to say that most probably in the future, there will be local agents, which will be quite simple and that can be easily implemented on any type of edge computing device. Okay. Another question, how 6G will allow motion control to be done wirelessly with extreme precision and reliability, enabling flexibility for the factories of the future? This is a very good question. I didn't mention motion control, which is the first column in the 5G SAA table, because it's most probably the most challenging from the communication viewpoint, the most challenging use case. It requires a latency of 0.1 milliseconds. So motion control requires super reliable technologies, latencies below 0.1 milliseconds. So if on one hand, again, it is sufficiently clear to me, I'm optimistic that 6G will provide such below 0.1 millisecond latency. How? Well, in principle, this is very simple. You can move from 5G, that will offer 1-2 milliseconds in a while, to 6G offering a latency of 0.1 millisecond in a very simple way. You scale everything in the technology by a factor of 10. You use a bandwidth which is 10 times larger. Most probably you have to go to frequency carriers which are 10 times larger, and everything will scale. Almost everything will scale. Actually, the propagation delay, which is a physical aspect, will not scale. And this is an issue at terahertz frequencies. But still, by scaling, let me give the simplest answer. By scaling, you can get 0.1 millisecond. It's just a matter of how large is the bandwidth, how large is the frequency carrier. And this is why in times we will consider 300 gigahertz as a frequency carrier with a frequency bandwidth in the order of 10 to 20 gigahertz. So it's just a technological aspects, nothing more than this. There's an implication, despite that everything scales, but the propagation delay is an issue. At distances like 2 meters from a UE, at terahertz frequencies, when you have to transmit short packets, the length, the duration of the packet is shorter than the propagation delay, even if it is picoseconds. So protocols must also be optimized. But still, new protocols and technologies with technological aspects that need to be solved, I think the latency within 3-4 years will be under control. But what about the reliability? This is much more difficult to achieve. There's a number of considerations to be made. Just let me mention one thing. We work very much on latency. Many scientists are offering papers discussing latency, but concerning the reliability with 9 nines, that's an issue. It's an issue even from the viewpoint of assessment, of performance assessment in a paper. How can you prove that a protocol stack, a scheduler, or whatever that you have designed has a reliability with 9 nines? There are two options. Either you have a mathematical model that describes your technology, and so you can assess the reliability with some whatever number of digits. But if it is simulation, and normally when you introduce many aspects in the study of a network, you have to refer to simulation. If you want to measure a reliability with 9 nines, it means that you need 10 to the 11, 10 to the 12 packets transmitted in your simulator. How many years are you going to wait until you have such level of simulation with billions of packets transmitted? This is a big issue. So how the reliability will be possible to measure, and what are the technologies which will ensure this level of reliability? From this viewpoint, I still don't have very clear ideas, I must say.
Okay. What do you think about the data privacy? Is a requirement for 6G feature factory networks?
Yes, definitely. What I was mentioning earlier is data security by architecture. Someone else calls it data privacy. It's a major fact. If we do not convince the managers of the automation industries that they can trust 100% our technologies to transmit their data or to handle their data, we will be unsuccessful in the deployment on a large scale of communication technologies inside the industry. So it will be an issue that must be properly tackled with, as I said, an integration of different approaches by the 6G standardization.
Okay. Next question. Regarding wireless communications in factory, when you remove the cables by wireless systems, interference can be challenging. What is your viewpoint about it?
I'm used to tell my PhD students, this is a joke, but it gives you the answer. I'm used to tell them the following. Oh, dear students, when you were a master student, you had to study my exam, whose title is Mobile Radio Networks, where I have dedicated 50% of it to the topic of interference, how to model, how to take into account interference, how to solve interference through protocols, and so on and so forth. Well, this is useless for you that are performing research in the field of wireless communications, because in the future, interference would be solved quite easily via beamforming. Because beamforming, which, as you know, is currently going to be implemented in 5G networks. Currently, many 5G networks are still using a sort of beamforming, but beamforming to a wide extent and to the level that is allowed in theory will be implemented in the next years by 5G and for sure by 6G. As long as you have a beam whose width is less than 1 degree or 1 degree, the probability that you get interference will become so low that it will be not an issue at all. This is why I say that part of the course is useless for you that are studying 6G.
Okay, the last question is about federated learning. So federated learning has demonstrated some weakness on security of the data, which means the original distribution could be inferred directly from the model. So how do you think will be the reaction of the industry partners knowing this aspect? Which option could come on the way?
Excellent question. As I said, we started working on this very recently from the viewpoint of privacy, because we were working on federated learning for other reasons. It's an excellent question. How much of the original data can be inferred by the neural, by stealing the neural network model? How much? Not 100%, for sure. How much? 90%, 80%, 70%, 20%? How much the relevance of the data that can be inferred is? We are entering here into the topic of importance awareness. Not all data, as well as not all the parameters of a neural network have the same importance to recreate somehow the model of the device, of the machine, and so on and so forth. So it is true that part of the data can be inferred by the neural network models, but I'm not sure whether it will be sufficient to really steal the knowledge, the information which is included in the game. To tell you what is the way I will assess, maybe in 1 year, 2 years from now, whether it is really secured or not, this concept, I have in mind how I will make it. I already told my students. I intend to organize next year an hackathon. We will implement on the machines at BREX this concept of the local agent. So we will transmit not the data, but the neural network parameters, and then we'll allow everyone to steal the neural network and try to infer the data to see whether the data they will be able to infer is of relevance or not to the companies that are building the automation machine. And then I will be able to tell you whether the data they will infer is actually sensitive or not. So far, I don't have an answer.
Okay, thank you so much. I think I don't have any more questions, and maybe we are running out of time. So once again, I would like to thank Professor Roberto Verdone for the time and for accepting the invitation. So this seminar has been recorded and it will be available very soon in the TII YouTube channel. So thank you, Professor. Thank you very much.
Thank you, and thank you for your very interesting and inspiring questions. Thank you.
Thank you very much. Bye-bye.